Now we're going to go back and relate some of these electrical concepts that I know seem a little foreign at first to some concepts that came up in the first semester of physics, the first term. And hopefully just going back and reestablishing these connections is going to help you make sense out of the relationships between electric field and electric potential and stored energy in a capacitor, things like that. So in the first term of physics, right at the start, I gave you the 5 key derivative relationships. And one of those, so this is from Physics 1. One of those was that the force as a function of X, let's say, this could be along any line that it's acting along where there's a plus and a minus. We'll see for gravity, I'm going to use Y instead, but this could just be any variable. Just remember that in all of these, we're talking about a positive direction and a negative direction along that line. And the force as a function of X is equal to negative derivative with respect to X of the potential energy. Okay, that's one of those key derivative relationships. And if you want to go the other direction, you can. So the change in potential energy is equal to negative integral from the starting position to the ending position of the force with respect to X. And then just remember that if you wanted to calculate the work from here, you could, because the work is equal to negative change in potential energy. Okay, this is only true for conservative forces. There's no such thing as potential energy for non-conservative forces. But when you're talking about electricity, it's all conservative forces. You can think of force fields and conservative forces as being synonyms. They mean the same thing. It means wherever you go, remember the field thing, wherever you go, whatever point in space you go to, there's sort of like a force waiting for the object there. That's the idea of a force field. And this change in potential energy, in Physics 1, we didn't talk about it this way, but you can think of this change in potential energy as the energy stored by moving the object from the position x1 to the position x2. Let's think about what this means in a gravitational field, because I think that's the one that's most natural to us. In order for this to be, in order to get a positive value for the change in potential energy, you always have to move the object against the force field in the opposite direction of the force. Okay. So let's say this is when the object is moved against the force. Okay. So what does it mean so if you move an object against the gravitational force, it means you're moving it up, okay? And so say you move an object 1 meter up. How can you think of that as stored potential energy? Well, you can do that just by holding the object in your hand. And if you have an object with mass and you lift it up 1 meter, you're storing that energy because all you have to do is move your hand away, move away the thing that's keeping it at that higher height, and all that energy is going to be returned to the object in the form of kinetic energy. Okay, so we don't talk about storing gravitational potential energy, but that you can think of it that way. If you move an object against the gravitational field, you're storing energy that you can use later. Okay, let's see how all these ideas come together mathematically in the case of a gravitational field. Um, so I'm going to use, for a gravitational field, I'm going to call the positive direction up, the negative direction down, like I usually do. And I'm going to use y as the variable instead of x, but that doesn't change anything about the meanings here. We could just as easily call it x. We're just not used to seeing up and down being x. And okay, so the force as a function of y. So remember, these all have to be given as functions. This can't be at a single location. Is equal to negative mg. Just saying that whatever y value you have, the force is mg and it's down in the negative direction. And let's calculate the change in potential energy, gravitational potential energy, in lifting an object and we'll say the object has a mass m, from the ground, and we'll call that y equals 0, that's where 0 will be, to a height h. Okay, and just remember that this change in potential energy, we're going to start thinking of that now as the stored energy. Okay, and we're making that connection because when we talk about capacitors, that is what we talk about as the stored energy. Well, the change in gravitational potential energy is negative the integral of the force as a function of y dy, and we are going to evaluate this from the height 0 to the height h. Okay. The two negative signs cancel out, and you get, so this is the integral from 0 to h of mg dy. If you take the integral of a constant, you get mgy evaluated from 0 to h. And so the stored energy from lifting this object is mgh minus mg times 0, which is just mgh. Okay, well, we already, in physics 1, we were given that function for potential energy, but you can see how the relationship gives us this, the relationship between forces and potential energy. And this, what we've figured out here is the stored energy, which means just remove the thing that's holding it up, and that energy will be, that stored energy will be converted into another form of energy, kinetic energy. We can do the same thing with a spring. I have energy on my mind. Example. Okay, so this time let's think of a spring and a mass. Although, interestingly, you know, the mass isn't going to come into this calculation. But the spring has a constant K. And let's say that we start with this object at its equilibrium position and then move it to a location L. Okay, so you start at the equilibrium position and then stretch this spring out a distance L. Let's think about a free body diagram. You have the weight force down. That's not going to come into it. There's a normal force up. That's not going to come into it. The only thing we care about is this spring force. And that's negative kx. Okay. And so the force as a function of x, and I'm going to have my positive going to the right, is equal to negative kx. And we want to calculate the stored energy, the energy that we're storing by stretching this spring out and moving this mass a distance L to the right. And again, this stored energy is the change in, this time, the spring potential energy. Well, I'm going to use this same derivative relationship. So the spring potential energy, the change in spring potential energy, is equal to negative integral from 0 to L, because we're starting at x equals 0 and ending at x equals L, of the force as a function of x dx. The same thing happens that happened before. The two negative signs cancel out, and we get the integral 0 to L of kx dx. The integral for, this is the polynomial rule for integrals, and so this integral comes out to be 1/2 kx squared. Again, in physics 1, I gave you that formula, but we can derive it directly from the force using the integral, evaluated from 0 to L. And so this stored spring energy, the energy that we're storing in this object by deforming the spring, is 1/2 kl squared minus 1/2 k times 0 squared. And so we just get 1/2 times k times L squared. And again, that's the stored energy that we get from deforming this spring. Now we can use this exact same approach for electrical fields. So let's say we'll use this exact same approach for the stored energy. I'm going to stop using the quotes now because this is the way we actually talk about energy in electric fields. So I'm going to start out by calculating a stored energy in a capacitor. The difference now is that we have some different terminology, and so you have to remember a couple other relationships. The first one is that the force as a function of x is equal to the electric field as a function of x times the charge that you're moving in that electric field. Okay, you can think of the charge of the particle you're moving around has the role that mass has in a gravitational field. Okay, so in order to figure out the force, we need to know the charge of that particle. And then the potential energy is the electric potential times that same charge. Okay, so to find these relationships, we're going to have to use these. And the reason that we do this in electric fields is because it turns out it's a lot more convenient to just have a way to talk about the field without knowing about the charge you're moving around in it, and then after the fact, put the charge in there. I guess if I had to imagine why that is, it's because we talk about the electric field staying constant as large numbers of different charges are moving around. So it's easier to do all the calculations first and then put the charge into it. Okay, so let's think about a capacitor. And we'll think of a positive plate on this side and a negative plate on this side. Remember, electric fields always go from a positive charge to a negative, which means that the electric field in this case goes this way. So that's our E. And remember that between parallel charged plates, this electric field is constant between those two plates. So let's say here we have parallel charged plates with a distance of 1 millimeter. And our electric field as a function of x is 150,000 newtons per coulomb. And just like I drew it over here, it's directed to the right. Okay, so any x value you put in there, well, it has to be between the two plates, but any x value you put in there, you get 150,000 newtons per coulomb pointing to the right. And we want to know what's the stored charge of moving one electron from the positive plate to the negative plate. So remember, to store energy, you always need to move your object against the field. So, well, you have to move it against the force that's being applied. So let's think about the force that's being applied. So the force on an electron that's in this field is a positive 150,000. It's positive because it's moving to the right. You know, our positive x direction is to the right, our negative is to the left. So we have our function E of x here, and we're multiplying it by the charge of an electron, which is negative 1.602 times 10 to the minus 19. And what you get is negative 2.403 times 10 to the minus 14 newtons. Okay, that's an impossibly small amount of force, but we're applying it to an impossibly small object. So, and that negative sign says that this force is directed to the left. So is this question asking us about a motion of the electron against the force? Yeah, we're moving this electron from the positive to the negative. So the force is in the negative x direction. The motion is in the positive x direction. And if you just think about the charges, it has to make sense because we're moving toward the thing that, we're moving towards the plate that's repelling the electron. So of course, that motion is against the force. Now that we have this force, we're doing exactly what we did in the gravitational case and the spring case. Our change in potential energy is equal to the negative integral. And we're moving from, I'll call the positive plate my x equals 0. So from 0 to the negative plate, 0.001 meters. And the force is negative 2.403 times 10 to the minus 14 newtons, integrating with respect to x. The two negative signs cancel out, and this comes out to be the integral from 0 to 0.001 of 2.403 times 10 to the minus 14 dx. Now just use the integral rules. This is a constant, and so we get 2.403 times 10 to the minus 14 x, evaluated from x equals 0 to x equals 0.001. And so we get this constant times 0.001 minus this constant times 0, and we get 2.403 times 10 to the minus 17 joules. Again, that's an impossibly small energy, but this is an electron. It's impossible to imagine how small this thing is. But notice we got the exact same result that we got in the case of the gravitational field and the spring force. Since we moved the object against the force being applied to it, we stored a positive charge. And then if we freed that charge to move again, it could turn all that energy back into another form of energy, like kinetic energy. Let's think about one more case. We've also done electrical problems using fixed charges. So let's say we have a fixed proton, and that's going to be at x equals 0. And we're going to move another proton from 1 millimeter away in the positive x direction to 0.5 millimeter away. just think about this intuitively for a second. Okay, these protons are going to repel each other. We have our fixed proton here, and we have this other proton here. And we're going to, so this one is fixed. And we're going to move this proton closer to it. Those two repel each other, so that is moving this proton against the force being applied to it. Okay, well, we have some calculations that we can do to calculate the force applied at a single instant. And what we want to do, again, is calculate the stored force due to this motion. Not the stored force, the stored energy due to this motion. Well, we have an expression for the force. So the force as a function of x is equal to the electric field times the charge of the particle we're moving around. In this case, that's a proton. And so this is 8.99 times 10 to the 9th times the absolute value of the fixed charge, divided by the distance squared, that's x squared in this case, and then multiplied by the charge that we're moving around, so that's 1.602 times 10 to the minus 19. Okay. And the way that we do this is we just use the absolute values and then use our intuition to figure out the direction. But this force is going to be in the positive x, so we're going to have a positive value for this force. And if you multiply this all together, you get that the force as a function of x is equal to not negative. This is equal to 2.3072. I'm just multiplying out the numbers, times 10 to the minus 46. The smallest number you've ever thought about, Times, I'm going to call it x to the negative 2 exponent. Okay. But the key thing is that for a positive x, this force is in the positive direction, which is what it needs to be. We know that this fixed charge is trying to push the moving charge to the right in the positive direction. Okay, so what's the stored energy in moving this object closer to the fixed proton, moving this moving proton closer to the fixed proton? The change in potential energy is equal to negative integral. And this time we're going from a distance of 1 millimeter away to a distance of 0.5 millimeter away. And our force is 2.3072 times 10 to the minus 46 times x to the minus 2 power dx. Well, when you integrate this thing that's to the negative 2 power, you get negative constant times x to the negative 1 power. That's the exponent rule again. And so what we get here is the negative from outside the integral times the negative that we get from the integration, negative 2.3072 times 10 to the minus 46 times x to the minus 1 power. So you could think of it as this constant divided by x. And we're evaluating it from 0.001 to 0.0005. Okay, so what we get is, I'm going to just rewrite this, those two negatives cancel out, and we have 2.3072 times 10 to the minus 46 divided by 0.0005 minus 2.3072 times 10 to the minus 46 divided by 0.001. And what we get is a stored energy of 2.3072 times 10 to the minus 43 joules. So again, in moving against the force, we have stored a positive amount of energy that later could be used as some other form of energy. Now, in the assigned problems, I'm going to have you do stuff like this, very much like this. I'm also going to have you do calculations where you go from the electric field to the electric potential. That's all of this same stuff, but just without multiplying by the moving charge. So just remember that you're still going to use this same approach, and you have to remember that the change in electric potential is the negative integral from the starting location to the ending location of the electric field dx. And these all have to be functions of x, remember, so I'll put that in here. But the approach is going to be the same. It's just that now, instead of talking about change in potential energy, you're dividing out the moving charge. Instead of talking about the talking about the force on the object, you're dividing out the moving charge to get the electric field.